Okay, here we go. So today, well, let's kick off with a run of the test suite. And this is a little bit different. This is, I think, taking away from the language rather than adding to, which is going to be kind of fun. So well, I'll spoil things a little bit. I've already done what we're about to do today, but I thought it would be really fun to do it live because it went really well. So here's the idea. We have built into our language this idea of an array. And I think the reason for this, the reason for this is that when I first started this project, my idea was to bake in some simple things that are always used in programming rather than try and make the language very generic. So I put arrays as a first class type, and this was going to be a dynamic growable array, kind of like a Python feel, right? Or even like a vector enclosure that's just there. It's like your built-in list and you don't even think about it. Same with optionals. I feel like optional values are so ubiquitous in applications programming. And I get they're not always the best choice for systems level stuff, but they're just so useful. I just built them in, right? So you can see here, like they're on the same order as struct. And if you know anything about type theory, structs and enums, like sum and product types, are pretty fundamental things. This never function type, these are all very different. And really, an array is just a struct, right? In this language, it's got a length and a capacity and a data pointer, and that's how it's implemented in the LLVM. And if we look, here are all the intrinsics, which means built into the compiler, needed to make the array work. So to get the length of an array is a special thing that only the compiler can do. What it does is it just does a gap on the struct and it grabs the length field, right? And this worked great when I was new to the project and really had no idea how to set any of this stuff up. And then the more things mature and evolve, the more I realized this is just a struct. So okay, let's see. We can't turn array into a struct though because we don't even have generics, right? That's the other thing too. The array that I built contains an inner type, right? And this is actually pretty easy to do as a compiler built-in. You just make a new type when you need one of a different element type. You pass that around and the compiler knows the element type. It's a lot harder to implement generics into the language, right? On the type level and function level. You really need both to do this. So if we look at the type we're trying to implement, we're really looking at something like this. This would be a struct with a length, a capacity. Now at the time, I didn't have unsigned integers. I didn't have this pointer type. And I didn't have generics on types. I didn't have generics on functions. So this couldn't be implemented in the language. But we now have pointers. We now have generics. We've done some videos implementing that stuff. We have structs and we have integers of all sizes. So if we look at bitwise, we've got U8s up through U64s and signed versions as well. So it feels like we've got all the ingredients, and I thought it would be fun to try to replace this built-in array with just a struct. Why do that? Well, you actually get to delete a bunch of code. So every time I do something in the compiler, I kind of need to handle every type of type and think about what should happen here. And that's a lot. Optional is the same here. So optional is really just an enum. In my last video, I said it's a struct because Copilot baited me into typing out like a struct definition. But optional is really an enum. This is really enum, none, or some t. So that would be all we need. And then we can still build in special syntax for these types, because what we can do is we can put their definitions in the prelude, which I'm going to rename to like the built-in or something. Built-ins being different than prelude. Built-ins being the things that the compiler can't even function without, and then prelude being things that are useful, right? So, right, what we can do is we can sort of expect to see optional type. We can expect to see this definition, and then we can like store its ID maybe as like a global, something we know the type, or we could expect it to be type ID 7 or whatever, right? And then say you can't reorder the built-ins, and then we can still build in functionality for optionals without having it be its own type of type. So we still have some custom code, but only as much as is unique, and then the rest that just kind of works like an enum can work like an enum. So that's the idea. The other option is to not even make it special at all and use type classes or abilities to do it all. So, what's one special thing we have on option? We have pattern matching. We have our coalescing. So we have like maybe it's like our maybe answer or a 42 in the case where this is an optional int, right? So this is just like JavaScript's double question mark operator. This only works on option now, but what we could do is we could say, well, this works on anything that implements the ability or else, where we just define a regular function and just special syntax. We could even go further and say you can define your own syntax and anchor it around an ability. And I think that would be really, really cool. And we're really starting to design like the everything programming language. And I think eventually it would just be Lisp. But the difference there would be the ability to define your own syntax that would not be as expressions, right? So I think that would be pretty neat to do. So where I started with, I'm going to make the most specific language with things baked in for getting stuff done. It's kind of like, well, I start to realize how tempting it is to make things not special. Like I understand why in a language like Scala, everything like option or as instance of, like all of this stuff is implemented in userland, basically. The language, despite the reputation of Scala as being big and bloated and a kitchen sink, the language is actually really elegant and minimal. And you can kind of do everything in it because the type system is very powerful. So anyway, it's enough rambling. The idea is to remove first class array and implement it using the language. So let's just get started here. First things first, let's start to try to write one in our prelude. So I said we were going to make one so we don't collide. Let's call it new array. And now we need to go look at our CodeGen file, because that's where the shape of an array actually lives. So I think I'm going to search for array struct. If I can type. Yeah, array struct type. Where'd you come from? Make array. So we have an array malloc here. That's special. Create array struct. This is mine. Okay. Length, capacity, data type. Built-in types, int. And then a pointer of the element type. And then we make a struct with those three fields. And then not packed. So let's emulate that. We have length, capacity, data. So we'll go len. And we can be explicit about the integer type here. And we'll be terse with len and cap. I like the symmetry too, I won't lie. And now data's pointer. So pointer is something that I've implemented recently. And it's replaced the raw pointer that I had before. This is actually a built-in. And built-ins they still have to be defined in the source. So they're done up here so that we have a span to point to, and so that it's less special in a few other ways. So pointer doesn't have a type attached to it. And this actually kind of mirrors how LLVM does pointers, where you only attach a type when you go to load from the memory address. You say what shape you expect it to be. It just makes it easy because we don't really need to store the type. We can supply it when we interact with it. And this pointer supports our multi-pointer use case as well through this internal ref at index. So given this pointer, which is just a U64 underneath, I can, and given a type t, I can index into it. So I can give you a reference to a t. And obviously this is extremely unsafe. And unsafety is something we'll kind of worry about later, but I think the idea is if you use anything unsafe, the compiler knows and it will mark your function as unsafe, and then we'll just sort of naturally infer where the boundaries are. And then maybe we'll require the user to write something or say, or to explicitly enable unsafe, but you need this stuff if you're going to do any of this in user land. So we have this ref at index, and then I was going to do memset. I think I might have done it up here. Yeah, I've done a few external functions as well, linking straight to libc. This isn't the long-term plan, but I have realloc and memset here, and I also have random for something else I was doing. And then I even have a built-in for assigning to a reference, because I just don't really feel like, for new programmers, like saying a equals x, like this is how you would typically assign a value to a pointer, and I just think it's absurd, like if you don't know what it means. So reference set is not ideal, but that's the idea, and that's what we're going to be using. I wouldn't mind it being a method like that. Actually, with my new pipe syntax, I could do, which is kind of neat. But anyway, this is our pointer. We have equals defined on it. We have null. That's about it. And here is our new array. So maybe we just, and I had a test function here, and then I had a whole to-do list of things. Let me check. I've kind of done, so trying to do this surface some prerequisites, and I did some work in the compiler. Yeah, I think we'll just shove this to the bottom because I don't want to lose it. And I am going to start over with this because it's not so important specifically what it does. All right, so we'd like to make a new array. We will call it X. And our type is called new array. And we will do, we'll do strings this time. Something a little more complicated. And that's going to be new array, new. And let's just make that size 0 for now. So we don't have a new. So let's go back to our prelude and write a new. So we have namespace new array. So in K1, we make a namespace with the same name as a type in the same scope, and it counts as its companion namespace, which lets us do stuff that belongs to this type. And that just happens automatically. So we need a new. New takes a type. So what we cannot do yet is take the generic once. So we'll add that later. This is going to be length. And we'll return a struct. Okay. Whoops. Let's see. Did that have anything that it shouldn't have had? Don't think so. Okay. Okay, so now what is our data? So we know it's subtype pointer. So how do we make one of these? I think we use our K1 malloc. And how much space do we need? Well, we need space for len t's. So we'll make that size bytes. And we'll say, we don't need a type here. And we'll say that size of t times len. And the clever reader will already be wondering what happens when this is 0. So worry about that later. Okay. We should return an I64 instead of unit. And look, we malloced 0 bytes and we compiled successfully. So that's neat. Now, malloc 0 is bad. If you've ever wondered what happens in Rust when I make an empty vec, does that allocate? Is that slow? Should I not? Should I use like option vec just to, to represent empty? So empty vecs don't allocate, and neither is our array going to. There's no point in calling malloc if we don't need any space yet. So what we will do is we'll say our length is 0, and we'll just say this is an internal contract. If the length is 0, then the pointer is null, and we shouldn't use it. And that's going to be fine because we're only going to interact with the data through the methods we define. So we're going to say val data. We can do if expressions. So if the length is not 0, then we're going to malloc size bytes. And if it is 0, then we're going to do null. And the capacity is the length, and the length is 0. So, and now we'll assert x.data. So we're going to assert that equals pointer null. And I'm also going to do something. So pointer can be cast to U64. We're going to assert that that's 0. And then we're going to assert that x.len is 0 and that x.cap is 0. So this is actually one error that has a bunch of causes. So this is kind of a bug. This is a bug, and this is better. This is the real error. So once I fix print error, we'll see expected expression but got colon. Pointer colon null. Oh, this is in prelude. Something wrong with this namespace function call? Oh, I made a boo-boo. There is, since, no, not just for colon. Hmm. We're going to do that for now. And then we're going to figure out. So we know we have a workaround. We have to parse struct values. Oh. This is parsing into a struct. Wow. I've never run into this. So look, I can just do a unit expression and then do this to get around this parsing bug. Yeah. Okay. Okay. Let me log that parsing bug. Parsing bug where first expr of block is namespace. Okay. And look, we passed, right? So let's assert the capacity is 1, and we have assert failed. Let's make a non-empty array. That's more interesting. We should see malloc 24, 16. Right. And we didn't see a malloc for our first array, so that's great. Let's actually work with our first one. And well, what do we want to do? Well, we need to grow it. So we're going to push. So we're going to push an element, which is going to exceed our length. So we're going to have to do grow, push. Yeah, grow and push here. So we're going to push a new string. We have to push hello. And now this is going to blow up. Method push does not exist. Not really blow up. So this is going to be self. This is our first method. And we'll just say crash unimplemented. For now, we're just going to test the type inference here. Unimplemented. So this is actually kind of a big deal because what this desugars to is new array push string x hello, which means that right we haven't passed that, so it has to look at x, see that it's a new array of string, and then unify new array string with the definition of push, which says I take a new array t and a type t, figures out that t is string, and then it's going to expect a string for t here. So what we'll do is that, and then we'll pass not a string here, and we'll see that we expect a string, but we get an I64. Now, if we don't hit the type, now I think what we'll see is that we couldn't solve the, yes, conflicting type parameters for type param t and call. Expected string, but got I64. It's like a drop the mic moment for me, but I know it's kind of table stakes to be able to just write x.push. So here we are, and we need to implement this. So we already know we have a special case if len is 0. So I'm just going to go ahead and say we'll just start writing. I don't know what the new yeah, we're just pushing 1, right? This is a very special case. So this is just going to be we'll just malloc a single, and then this returns a pointer. So we kind of want to do self.data equals. And then we could say new data. And this is our other scenario. So if our length is equal to our capacity, it should never exceed it. And if it's less, then we have at least 1. So this would mean that the length is 4 and the capacity is 4. And we're trying to add a 5th. So then what we'll do is we will realloc. We'll recall what realloc takes. The pointer and just the size. So this is going to be self.data, and then we're going to double. So I actually have a okay. I think I'm going to keep going. I have a better implementation of this from last time I did it. I just got a little bit luckier. So we'll just go through here, and then we're going to fix it. So the new capacity needs to be, we're going to double our capacity if we don't have room. And in this scenario, we also need to increase our capacity just to 1. Our new capacity is capacity times 2. We're going to realloc, and then that's going to be size of t. And this is how much space we need. And then that's going to be self.data. That's new data. And we're going to make sure to assign it. So self data, new data. We'll go ahead and explicitly return unit. Self.cap. So the problem is we don't have new cap. So we could do this in each branch. This is not good. And now we need to actually push the element. So this is going to be self.set, which we haven't implemented yet. And that's going to be where we actually set the element that we know we now have capacity for. Okay, so we're doing 2 things in here. We're growing and we're pushing. So let's implement grow as its own thing. And the idea, and take new array, right. And I'm just going to copy a little bit from my notes here for the sake of video. So if all we have to do is grow, it's pretty simple. If the capacity was 0, it's now 1. Otherwise, we're going to double it. This makes sense. You can't just double it from 0. It'll never increase. So now we're going to say if self.data is null. I wonder if we have is null. Is null. Let's try that. No idea if that'll work. And then this is our realloc, which we had right. And check for failures. So if that's still null, then realloc failed or malloc failed. Okay. And that's how we grow. And now push becomes a little bit simpler. Let's think about this. So if the length is equal, then we need to grow. And now we're going to set, and I think, yep, that is, and we need to assign to self.length. And it looks like we're going to need to implement set as well. So we need to get the t pointer. So this is where we actually access data. So gotta stop saying so. We want this to be of type t reference. We need to do a length check. And then this is reference set tref lm. And now just get, which is actually the same up till here. And now we just need to dereference the value. Which means, let's factor this out. This will be get ref, maybe? I think I called this, yeah, I think I called this get ref. Let's see if this can infer without the hint. Stress test the type system a little. The fact that this is stress testing the type system is funny, but you have to start somewhere. Now set and get look pretty nice. So we just wrote a lot of code. It's not going to compile. Let's see how good our compiler is helping us. 158. Missing semicolon. Hey, only one syntax error. Okay, so this is actually a place where I crash when assigning, looks like assigning to a reference. Expert L value, yep. So I was hoping to get, okay, so let's add a to do. So we'll be fancy and we'll say we got an ICE. We'll say ICE when assigning to struct member when struct is not a reference. So the way this language works is actually that everything is a value and is passed by value unless you use a reference. So when we take a new array of t, what we're actually doing is the caller, if the caller has a new array t and then they pass it into getref, then we're actually making a copy of this struct, which means if we modify length and capacity, we're only modifying our copy, which is not what we want. So I actually don't even allow you to mutate struct members. Oh, I crashed, but don't expect to allow you to mutate struct members unless you have a reference. So what we actually need here, well, this is fine because this doesn't mutate. So we don't need a pointer to new array, but for set, no, we still don't. But for grow, this needs to be a pointer to new array. And for push as well, we need a pointer. And for set, we are not going to touch length or capacity. We're just going to mutate data pointed to by that pointer, so we don't touch the struct. So we actually don't need it by reference for set. Looking at my reference impl, yeah, I didn't take that by reference either. Yeah, 39 minutes. Wow, time flies. Well, let's see if that worked. Okay, so we're back in our client code, and it expects a pointer, but we got a new array. So we actually need a pointer. Now in my prelude, I recently added a new function. And I don't like this. We're not going to keep this around. This is very Java or C++, where we expect to just keep allocate everything one by one. That's not the plan. But I did need a way to get a sane reference to something that's not going to be stack bound. So we do have new. It's kind of neat. If you look at it, it's implemented entirely in userland. We malloc the size of t. We interpret that pointer as a reference to t. We set the value, and then we return t. So what we'll do is just call new here. And we'll see how that does. Okay, so we couldn't infer. And this is because, well, there's a type hint of string here, but it's actually the wrong type. So that probably won't help us much. And we still can't infer everything. This is kind of tough, but let's just say new string, and then we'll leave this off, and that should just still infer correctly. Yeah, so now we have a pointer to a a new array of string, and I could actually prove that, but I guess this proves it well enough. So index out of bounds. So that's not really what we wanted. Well, this could really only be coming from one place. Okay, so we call push. And if start length is cap, which it is, then we call grow. We increase length, and then we call set at the wrong one. That needs to be start length. And there we go. So we malloced a second time. So yes, now that we have new, we're allocating our array, which is 24, because we have 8 plus 8 plus 8. And then we push our string, which allocates space for one string. And we'll push builder, and we'll see that we didn't allocate again, which worries me a bit. That didn't look good. That was some kind of a loop. Same thing again. Let's assert on our length and capacity after this first push. Okay. Seems like we're okay now. But our the length should be 2 after this, and the capacity also 2. 1 times 2. Yeah. Let's make sure this is compiling. Yeah, it is. I'm a little suspicious. We're not printing, and we're not allocating again. Let's hop in here. So I'm gonna look at my push. Look at my grow real quick. Mm-hmm. And then new. Let's switch to characters to make sure it's not an issue with strings. Sure. Okay. I think it's a problem with strings. Well, we'll figure that out later, I guess. Let's keep going with primitives here. Let's push again. And hopefully length will be 3 and capacity will now be 4 because it will have doubled. And then we'll get 2 as well, which should be C. So we should get A, B, C. Okay, but we're not. We're allocating 1 byte and then we're not allocating again. So I think it just happens to work because it's smaller, because it's over allocating for us. So what is going on here? Realloc. If data is null, one times size of t, or that's going to be new cap times size of t. We're going to malloc new size, or we're going to realloc self.data new size. We could whip out the debugger. Try to figure out why malloc isn't being called. Oh, because it's calling realloc. Okay. It is. It is working. But not with strings. That's okay. Let's try set. So we see that C is 2, or 2 is C. Let's set it to Z, and then print that out. So we should have A, B, C, Z. Now let's go out of bounds. And we're out of bounds. So with that, I think we've reached feature parity with the old internal array. If I look at these intrinsics, getting the length we can do, getting the capacity, set and get element, set length we don't even need something special for, and we don't really worry about it from outside, and new and grow. Our only problem is that it didn't work with strings. So let's implement first and last real quick, because those were the only nice functions that we had on our old array. So we're gonna do fun first, and that's gonna be an optional t. So I really like his empty. I know it's trivial, but it's just really nice. Yeah, I think I can just do len 0. Doesn't have to also check capacity or anything like that. This will automatically wrap it in an optional sum because we're expecting an option of t here. And then for this, we can just do none because we're expecting an option of t. Let's compile that. Good to go. So we'll assert three ways of asserting it's null. Yeah, nice. And down here, first, for here it'll be C. If we're non-empty, then there will always be something at length -1 because either length will be 1 and that will be index 0, or length will be more than 1 and it'll be fine. So that is last. Okay, so there's no equality on options. So what I will do is I will force unwrap these. And there we go. We should implement equals on options, but we can't do generic abilities. Because this would be impl equals for, yeah. We could do it. It's not, huh. No, it's very different. Okay. Anyway. So this is a little sneak peek sort of behind the scenes of the things I did. So when I first built this, I actually, to get it to compile, if you're interested in sort of the internals, what I had to do is I had to put a T here. And so what I made it, I called it phantom, just like Rust's phantom data. And I made it an optional T so that I could put none. Because my type system, the way it was inferring and the way it did a lot of things was by looking for type variables. And because the T didn't appear anywhere in the struct, a lot of things didn't work. One, it didn't pick it up as generic. Another, it didn't pick it up as containing a T in other places, so weren't able to infer anything. But what I ended up doing is I'm now storing specially, like every time I instantiate a struct, if I'm instantiating it as an instance of this generic, then I make sure and tag that struct as like a child of it. And then when I'm doing solving for generic variables or other things like checking if a type has type variables, instead of walking the struct, I first check, is this a generic instantiation? So what I end up getting to look at for the point of that analysis is I don't end up having to look at the struct inside. I actually just kind of get to look at new array of T, the way you would conceptually think about it. So when I'm going to infer, here on a call to get ref, I don't see that self I no longer see that self is of type struct, len u64, cap u64, data pointer, phantom, t optional, and then I see the t. What the code now actually sees is it actually just sees new array of t, because it knows to check if we're doing generic stuff basically. So I can actually go ahead and show that. So this is in solve generic params. So I have a new special case. So this is the old implementation where like, okay, if they're both references, if they're both optionals, this is another reason why I want to get rid of these special types, right? There's nothing really happening here that isn't true of an enum. Same for array. But here's the new one where we say, well, if the thing you passed and the argument are both instances of a generic, then we can do something much simpler where we don't really care what the generic expands to. We're just going to say, like, are all the type args the same? And is the base generic the same? So this just lets the code basically say, hey, I want a new array of t, I got a new array of int. Instead of saying, oh, I got a len cap data pointer blah of t, and then I gotta write looking through the struct. So I hope that makes sense. Kind of just making it work the way your brain would work when you look at these types. But the way the type system works, this is actually really a function. It kind of calls new array with this t, which is different than this t, because this is a function. So we're making a new copy of new array every time we call any of these. And that copy of new array is really just a struct. But now it's a struct that knows it came from new array, and we're checking that like origin and using that because it's just a much simpler way to do this stuff. So that was getting rid of phantom type. Here, did some stuff with type inference and hinting as well to get some of this stuff working where we don't have to pass types in. Like I kind of called out, I added the constant for null. I implemented equals on pointers. I did that new function as well. I did the reference set as preparation for this as well, which I actually already, no, I didn't. I had a way to reassign a variable. I didn't have a way to reassign the memory pointed to by a reference. So the equivalent of this of in C, right? So I just made it a built-in function to not have more special syntax. Whew. So I think that's it for now. I think anyone who's written their own dynamic array in C a million times is going to look at this and one, laugh at how I struggled through it, and two, point out, there's all sorts of things that make for a good dynamic array. We're doing the most naive thing here, right? Double capacity, really simple. But the point is, all the primitives are here. We could make this do quite a lot. I think we have everything we need to do a built-in hash map too, which is really fun. I'm going to take a quick break, and then I think we're going to come back for part 2, which is the really fun part of actually ripping all of the array code out of the compiler. The only thing we don't support yet is the built-in array supports these literals. So we're going to need to make these literals point to our new array too. That'll be kind of fun. Yeah, till next time.